Okay, let me open another books here we have.
Yeah.
So, okay. Okay, now here we have the concept of one-sided limits. Okay.
Mm-hmm. Yeah, we will just start from where we left. I mean, like, because
Mm-hmm.
uh, yeah, let's just go from continuity next class.
Continuity.
2.5. Continuity.
Continuity. 2.5. Okay.
Because the one-sided limit we are actually covered it already. We had done it in
Hmm.
that question, right?
Yeah. Yeah.
Remember?
Yeah. That's fine. So here we have now continuity basically.
Page 76.
Yeah. Yeah. That's fine. So continuity here we have now.
Mm-hmm.
So let me take an just a snapshot here. If you want the recordings also, I can send you the recording of lecture also. The lectures are recorded right now.
Yeah.
Okay, that's
Okay.
fine. That's fine. That's fine. So here we have now this graph is given here. Basically, the function is not continuous at x equal to 1, x equal to 2, and x equal to 4. Here we have. I mean, you already know continuity. Here we have. I already given you a hint with regarding. Here we have one point discontinuity. Here we have. Here we have. This is the point discontinuity.
Yeah.
Then again here we have a point discontinuity. You know already, I mean, what is meant by continuous and not continuous? For continuity, basically, we have here. For continuous at any point, we have here basically. Now, for discontinuity, here we have the left hand limit equal to right hand limit. Are you getting this point? At this point, here we have the left hand limit equals right hand limit, but
Yeah.
they are not equal to limit at the point, but not equal to limit at the point. So, it makes the function discontinuous.
Okay. So continuity is only when right hand
Yes,
limit
equal
at the
right hand
point.
limit equals limit at the point.
Yeah. Okay.
Perfect statement. Now you can see, is this point continuous here at x equal to 3? Is it continuous?
Um. Yes, it is.
It is continuous here we have. That's perfect. So at this point here is coming out to be complete continuous here we have at x equal to 3. Yeah. And about this, again here we have a point discontinuity here we have at x equal to 4.
At x equal to 4, it is not. Uh,
Yeah, it is not continuous. Here we have one point discontinuity here we have at x equal to 4. So, I mean, here we have some definitions regarding that.
Hello.
Yes.
Yeah, it's very the connection is quite bad. Can you repeat that?
Yeah, I'm just not doing a snapshot here from the book only regarding the definition of continuity. So, definition here we have now the function f is continuous at c if limit x tend to c fx is equal to f of c.
Yeah.
The function f is right continuous at c or continuous from the right if limit x tend to c plus fx is equal to f of c.
Yeah.
The function f is left continuous at c if limit x tend to c minus fx is equal to fc. Okay.
Yeah.
So left continuous means we have left hand limit equal to limit at the point. Right continuous at c means that the limit from the right continuous from the right basically. On here we have continuous at c, that means limit at the point is equal to value of the function at c.
Yeah.
I'm again repeating. See here we have, I'm again repeating, through the graph here only. Here we have, at this point here we have the continuity from the right, because we have here at this point limit, it's an important point, x into c plus here we have fx is equal to f of c. Here we have now continuity from the left. Here we have basically at this point here we have now limit x tend to c minus is equal to, here we have f of or b minus here we have is equal to f of b. Okay, x here we have. So that is, here we have the left hand limit equal to the value of the function at point b. At this point we have, there is a two-sided continuity. At this point here we have left hand limit equals right hand limit equals limit at the point, that is equal to value of function. So limit at the point is equal to value of function at this point. That is known as, here we have two-sided continuity. Here we have.
Yeah. So, given that, for example,
Uh-huh.
you have a range, right? You have x going from 0 to 10,
Mm-hmm.
and the line is continuous. It's just a straight line. X is equal to 1.
Mm-hmm.
The entire.
Yeah.
Then the limit at x is equal to 10, it will be 1 only, right? That at that point it is non-discontinuous, because the right hand side is not there. For example, no, it's not like all three of them.
You can say, you can say that is continuous from the left. You can say that.
Yeah, but it is not.
It is not, it is not two-sided continuity. See, here again, here we have good topic. Yeah. Yeah.
It is just
One-sided. Yeah. So here we have either continuous from the left,
Yeah.
continuous from the left here we have, or it is continuous from the right, or we have the two-sided continuity. Here we have now continuous from left, here we have continuous from right, or here we have two-sided continuity. Here we have.
Yeah.
Okay, so now let's do some examples here, and example 2 and 3, and let's discuss them. Now here we have example 2 basically. Example 2 says that the function f(x) is equal to square root 4 minus x square is continuous over its domain minus 2 to 2. Here we have. So this is your y-axis and this is your x. Here we have. So we have now y is equal to square root 4 minus x square, or you have here x square plus y square is equal to 4, right? So it is continuous over its domain minus 2 to 2. So here we are now coming out with this. So here we are now minus 2 to 2 is coming out to be, here we have this function is continuous over domain. We have minus 2 to 2. Here we have. Now it is right continuous at x equal to minus 2 at this point. It is right continuous, and at this point it is left continuous. Here we have. So I think it's just illustration is given. Just an illustration is given. Okay. Anyways, no issue. Now next we have so example 3. Here we have now the unit step function ux is right continuous at x equal to 0 at this point. Right continuous. I'm just talking about this one here. Right continuous. and but is neither left continuous nor continuous there. I mean, how we can say that at x equal to 0 it is right continuous but neither left continuous nor continuous? Can you tell that? And what is meant by a jump discontinuity?
Yeah, because the there is continuing from the right side. If you come, there is continuity,
Hmm.
but there's a jump 0, right? So there is from the left side there is nothing going to 1.
Okay.
It is only going to 0.
Hmm.
From the left side, if you're viewing it, it
Hmm.
will have a link 0, and
Yeah.
from right side it will be 1.
Okay.
Because both were not the same, it is not continuous.
Okay. Absolutely. So here we have the values included 1 basically. Here we have this value there, 1 we have here. So therefore it is right continuous from the right basically. It is continuous from the right we have.
Yeah.
Now here we have one continuity test basically we have. So f of c exists, the first condition. A function fx is continuous at a point x equal to c if and only if it meets the following three conditions. The first one is f of c exists.
Yeah.
Second one here we have now limit x tend to c f of x exists.
Yeah.
Third here we have now limit x tend to c f of x is equal to f of c. So this we have actually. F of c exists here we have now. The limit x tend to c f of x exists. Then we have now limit x tend to c f of x is equal to f of c. If this three condition exists, we can say the function f is continuous at a point x is equal to c.
Okay.
Now here we have an example number 4. So let's discuss this now. Now here we have example 4 basically. The function here we have y is equal to, it is the greatest integer function. It is the greatest integer function. Now first tell me what is meant by the greatest integer function we have. What is meant by the greatest integer function?
Great function.
Mhm.
That is actually within any span,
Mhm.
within any range,
Mhm.
domain, within any domain,
Mhm.
you're rounding it up to the nearest integer. That's it.
I mean, what is meant by greatest integer actually? Why the name is given greatest integer function? Why the name is greatest integer?
Essentially, see if you have 0.5, the greatest integer is 1. That is
Okay.
the integer that you're rounding. You can either round it to 0 or you can round it to 1.
Okay.
Even if you're at 0.99, you can also round it down to 0 or 1.
Mhm.
We have it to an integer. Now the greatest of that one. That is the thing.
Okay, and so you're saying that if it is x equal to 0.99 for example, you round it to greatest integer, that is 1 basically. Now if we have, let's say, x is equal to 1.1, then what will you value of y? If x 2, yes, you got the point now. The point is, if we take, let's say, here in this range we talk about here, in this domain, if we take x is equal to here 0.2 for example, at 0.2 we will take, not here we have two integers involved, one is 0, one is 1. Now out of 0 and 1, which one is greatest integer? Out of 0 and 1, which one is greatest integer? 1 is there.
One.
So we take the value as 1 here.
No, it's the opposite here. Now look, if because the greatest integer function it is the opposite.
Okay.
That's the thing of what you have just told me. Because look where the thing is. At 0.5, the value will be 0 only. At 1.5, the value will be 1 only. At 2.5, value will be 2 only.
Okay. So I mean, yeah. Now here we have one more question. Why it is opposite actually? Why the name then greatest integer? I mean, then it should be smallest integer. I mean, if you take 0.2, the value y is taken as 0 only here. The name should be smallest integer then.
Yeah, I don't know. Well, yeah, it's bad naming or
Now let me just explain it to you actually. What's the logic behind this? Let me talk about here. The simple one here we have 0, right? Here we have 1.
yeah,
Okay?
yes,
That is the open one. Here we have 0 to 1. And this coming out to be here we have this one. Okay? Now, here we have actually, see, leave every other integer basically. Now, let's suppose we talk about here at x equal to 1. At x equal to 1. Now, at x equal to 1, what about the value of y? My question is, at x equal to 1, what is the value of y?
equal to 1, y is equal to 1.
At x equal to 1, we have y is equal to 1. Now, at x equal to 1, we have y equal to 1. That means at the greatest integer 0 and 1, it is taking the value of greatest integer. That is 1 only. Are you getting it now?
Only at the integer.
Only at the integer, greatest integer actually, yeah. That means at x equal to 0, that is the greatest integer between minus 1 and 0. It will take the value not as minus 1, it will take the value as 0. That's how the name is greatest integer function.
But you're looking at it from the left side.
In actually, what we do actually, at the greatest integer, we take it right continuous, not the left continuous. At the greatest integer, we take it right continuous. Okay, now here we have 2 basically. So again here we have now the value of 2 here we have. So at x equal to 2 now here we have. What about this value? At x equal to again it will take the right continuous here we have.
Yeah.
At x equal to here we have, it is right continuous basically.
Yes.
Right?
Yeah.
So this we have here. Now what about next?
What do you mean with that?
Okay. Now you understand the meaning of now you understand the meaning of greatest integer function. Now you understand the meaning of greatest integer function.
Yeah. It's this diagram.
Absolutely, yeah. So here we have at the greatest integer, it is right continuous. Again here we have right continuous. Again here we have right continuous. Again here we have now right continuous. All right. Now let's talk about here the smallest integer function. Okay. So you know now draw a graph here for this smallest integer function. Let's draw the graph here for this smallest integer function here we have.
So it will have control.
Mm-hmm.
Right. So you have one,
Mm-hmm.
so what you'll have is smallest integer function. At 0, the function will be 0 only.
Mm-hmm.
Right. but it will be like this.
Okay, keep on going, keep on going. That's fine.
Yeah, something like that.
Mm-hmm.
So essentially, your take at you it's still right continuous,
Mm-hmm.
but the value jumps down
Okay.
um, by one every time you look from the right.
All right, all right, all right. Your argument is so at
So
1.
actually add yeah add
No,
zero.
it is smallest integer, right? So add 0, it is smallest integer here we have. So add 0, it will take 0. That's correct. Add minus 1, take minus 1. That's correct. And here we have at 1. I'm sorry, at 1, it will take 1. That's correct. And at 2, uh,
It's two also.
it's 2 only. Okay.
Yeah, but everything else, I mean, like, so if it's like 1.5, it will still be two.
Okay, okay, let me check, let me check. So between 1 and 2 here we have, between 1 and 2 here, if it is at 1 basically, you'll take the value as 1, right? Now between 2 and 3, 2 and 3, if you just compare here, you'll take the value as 2. That's perfect, yeah. And you can
No, no.
see, yeah, yeah,
This
yeah.
is one. This is one. This is two.
Yeah, that's what I'm saying. Between 2
Yeah,
and
but
3, between 2 and 3, it will take 2.
between one and two,
No,
the
no,
value is two.
no, no, between 2 and 3 I'm talking about. 2 and 3.
Correct, sir. But it's not there. No, I have drawn it wrong then.
No, no, at 2. It is 2 only, no?
Yeah. So
Yeah.
between one and two, what is it?
No, no, I'm saying between 1 and 2, if we are at smallest integer 1, it will take 1. That's fine.
Yeah.
Now between 2 and 3, if we had smallest integer 2, it will take 2.
Yeah. Yeah, and then three.
Yeah, that is perfect. You have drawn it right, verified, yeah.
Okay.
Now, can you tell me it is which discontinuity? Two-sided, right-sided or left-sided?
It is left-sided discontinuous.
Left-sided discontinuity, absolutely. It is continuous from the left, basically. Perfect, yeah. My answer is clear, yeah.
It's
I mean,
continuous from the right-sided discontinuous.
left-sided.
No, right-sided discontinuity, left-sided continuity.
Oh, okay, okay. Right-sided discontinuity. Okay. Actually, yeah, yeah. Let me come definition here. Yeah, wait, wait, wait. Please wait. Where it goes? Here. Actually, we never say right-side discontinuity. We say either right continuous at C, okay, or we say continuous from the right. That's how mathematically it is defined, okay.
It is not.
Yeah, yeah. But your logic is correct. But mathematically, we define like this: right continuous as C or continuous from the right. Yeah. Okay, perfect.
So that graph is wait what the graph that I just drew here.
Yeah.
This one uh, is it continuous from the right or not?
Which one?
It is right.
This one. This is continuous on the left.
This graph is not continuous from the right.
No. Yeah, yeah. It is not continuous on the right. It is continuous from the left.
Okay.
Yeah, yeah. Okay. Next we have some more discontinuity here. We have jump, infinite, oscillating discontinuity here we have. So let's discuss them once. It is continuous here, right? This one is point discontinuity, right? This one again here we have point discontinuity. This one is jump discontinuity. This one is infinite. This is known as here infinite discontinuity or asymptotic discontinuity. Infinite or asymptotic discontinuity here we have. This one is oscillating discontinuity. Next we have now some properties of continuous functions. Okay.
Yeah.
I mean, so let me just take a snapshot here. So here we have now properties of continuous functions. Here we have if two functions f and g are continuous at x equal to c, and the following algebraic combinations are continuous at x equal to c. Sums we have f plus g, differences is f minus g, constant multiples we have k into f. Here we have products we have f into g, then quotients we have here f by g basically, powers is f to the power n, roots is function, then nth root. Okay, simple algebraic we have like 2 plus 3, 2 minus 3, 2 into 3,
Yeah, that's fine.
and 2 by 3 here we have 2 to the power 5, or we have a third root of 2, cube root of 2, like this. So basic algebra we have for the continuous functions. Now let's just discuss examples here we have. It is quite basic mathematics here. Here we have an example 6 and example 7 here we have. So just go through them and read them. Any question, any problem, please let me know. Example 6 and example 7.
Yeah. Okay. Function model of x is greater than 0. Why would it be continuous only if it is greater than 0? Oh no, it's not. No, not here. We have finally at the origin. Right. Function y equals sin x minus cos x. Example 11. Both functions are in bracket f. For example, y tan x continues dot okay, so they're saying tan x is continuous because sin x and cos x are continuous.
Okay. See, all right. So
Hello?
yeah. So any doubt in this question? Yeah.
Doesn't tan x is continuous because sin x and cos x are continuous? Okay.
No, not like that. Not like that. Let me tell the graph here. Okay.
Yeah, but they're saying, in fact, for all six trigonometric functions, then are continuous wherever they are defined.
Mm-hmm.
Um, because when it's undefined, they're not continuous.
I mean, whether something is defined or not, but 10x graph is not continuous. It has the infinite or asymptotic discontinuity.
Yeah, that is there, but like it is saying that, for example, y is equal to tan x is
Mm-hmm.
continuous dot union minus by 2 pi by 2
Yeah.
union pi by 2 dot.
Mm-hmm.
What is dot?
Let me explain this to you. Here we have 10x, right?
Yeah,
Here we have x, the graph going like this. Here we have this asymptotic line here we have. There's a graph like this here we have. And this line here we have now. This coming out to be here we have at this 0 here you have, and then pi by 2, then 3 pi by 2, then 5 pi by 2, right? So you can say domain, as if they're talking about domain here we have for which the function is defined. Domain here we have 0 to pi by 2, right? For domain is we have s greater than 0. 0 to pi by 2, then union we have here pi by 2 to 3 pi by 2. Then again we have union here 3 pi by 2 to 5 pi by 2. So this is how it is defined domain. But the function is here we have the asymptotic discontinuity here we have. Asymptotic discontinuity.
asymptotic discontinuity. Yeah, because it is not approaching the same limit also.
Okay. Because it has infinite value here we have.
Yeah, because if the function was going like this,
Mm-hmm.
like you have something like this.
Yeah.
Something like that, then you can say the limit at this point, say x equals 0,
Mm-hmm.
at that point is infinity, minus infinity,
Yeah.
because it goes towards minus infinity.
Yeah.
Can you say that?
I mean, can you repeat that point? I mean, can you repeat your question?
Sorry, yeah.
Can you repeat your question,
Because
please?
you can see this diagram on the right side.
Yeah.
Now, if this is going towards minus infinity
Mm-hmm.
at x is equal on both sides, you can say the
Yeah.
limit at x is equal to 0 is minus infinity, right?
Yeah.
That you can say.
No, we can say actually limit x tend to pi by 2, not 0, and 10x, that is not defined. That we can say. It is actually 1 by 0, not defined. 1 by 0, we draw the graph like that. 1 by 0.
That is okay. But
Yeah.
I'm saying that you are saying because both of them are going in opposite directions from this side. And
There's a reason. There's a reason actually.
yeah, it's because this is going this way,
Yeah.
that is going this way,
Yeah.
right? So they are going towards infinity and minus infinity.
Yeah.
Therefore, there is no limit.
Mm-hmm.
But if the both of them were going like this
Mm-hmm.
towards infinity, then you could say limit is infinity, right?
Yes. Yes. I got your point now. Yeah. You're right. Yeah.
That's
Yeah. Yeah. Perfect. Hmm. Like in the last example. In this, here we have limit is infinity.
yeah.
Here it is. Here we have oscillating discontinuity for sine 1 by x. So here we have now it's coming out to be now. Here we have now composites. The composites here we have all composites of continuous functions are continuous, right? The idea is that if fx is continuous at x equal to c and gx is continuous at x equal to fc, then g of f is continuous at x equal to c. Here we have. So limit as x tend to c is g of fc. See, diagram shows that at a constant c, find the function at the value of c. Here we have. So we get fc, right? And then g of f of c basically. Move like this. You will get g of f of c. Here we have continuous at f of c. So we have a composite here. One is this function, and this function here we have. Compose them. You get the composite function g of f. A composite function here we have.
Yeah.
So composite function here we have g of f of c. That is here this way. Here we have g of f of c. So this theorem here we have. Now next. Now example 8 here we have. I would like you to go through this by yourself. Any doubts, let me know. Okay. Let me just paste a snapshot here. Now here we have example 8 basically. So example 8, here we have 4 points A, B, C and D. You have to just go to solution here and find out any problem, let me know.
Okay. Y is equal to root of x squared minus 2x minus 5. Okay. Means square. Okay. Square root of root of the continuous. Okay. Right. So what they're saying is this A part is f of g of x, where g of x is x square minus 2x minus 5,
Mm-hmm.
and f of x is root x,
Okay.
right? And given that g of x, because x square minus 2x minus 5, that is continuous,
Mm-hmm.
and root x is also continuous.
Okay.
Therefore the multiplication is also continuous.
You're right, yeah. Yeah. Composite function, yeah.
Yeah. And the same thing with the other ones, I guess. Then
Yeah.
you would have the modulus of that for b, x to the power 2 by 3 and 1 by x by 4, like x4. You can have like g of x is 1 over 1 plus x to the power 4.
Mm-hmm.
That is numerator of the cube root. The denominator is an everywhere positive polynomial. Okay. Therefore, the quotient is continuous.
Uh-huh.
Because they're saying this is positive.
Yeah.
Uh, 2 by 3. Okay. For B, I don't like what Hello?
Yeah.
Hello?
Hello. Yeah.
Yeah, for D, it is again f of g of x, where g of x is 1 by 1 plus x to the power 4.
Hmm.
And 1 plus x to the power 4, it is always positive, because power 4 is always positive.
हाँ मैं
X
पढ़ा रहा हूँ
divided
क्लास है.
by
हाँ 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 ठीक है अभी ले आओ. Yes, yes, yes.
So I mean, like the denominator is always positive. So
Okay.
1 divided by 1 plus x to the power 4
हाँ
is
हाँ.
always, given that x to the power 4 is also positive.
-1. Yeah, you're right. Yeah.
Uh, and then x to the power
2/3 also continuous. Continuous. Yeah.
that is a continuous one. I don't know how it looks, but it's continuous.
That's fine. That's fine. So f by g is continuous, right?
Yeah.
C part now. This one.
The c part, same thing. You have to say x by x minus 2
Mm-hmm.
divided by x square minus 2. That is the same as uh, that is a function.
Mm-hmm.
That is always positive and it's continuous also. But okay, how do you know if it's continuous or not? Just by looking at it.
This one. I mean, this will be here given as modulus x minus 2 whole divided by modulus, here we have x square minus 2. So modulus x minus 2 here we have whole divided by modulus, here we have x square minus 2. Right. So I mean, this continuous, right? And this one is also continuous. So we have the composite is also continuous here we have. We know because the absolute value function is continuous.
Composite, you mean composite is g times x, not g divided by
No. In this case, we have composite. This is f. This will be g. So I mean, this will be
composite is g dot x, right? G dot f. That is
um.
to have, if you're having a fraction, g of x is
No,
1 divided by modulus.
we can say f is continuous, right?
Yeah,
Then g is continuous.
g is continuous, but what is g? What is g in this case? What is g?
G is modulus x square minus 2.
No, I would argue against that. I would say g is equal to 1 divided by that.
I mean that if you say here g is 1 divided by that, then you can say f into g is continuous.
Yeah.
If you say f into g, then you can say yeah.
I don't know if f divided by g is also continuous. I don't know. It probably is.
No, it is. It
But,
is. Whenever we have two function f and g, f by g if f is continuous, g is continuous, then f by g is also continuous, provided g of x is not equal to 0. Provided g of x is not equal to 0.
right.
Yeah.
Also, so then any mathematical thing, so like f to the power g,
Hmm.
that is also continuous,
Hmm.
provided it's not something that disobeys the continuity,
Okay.
right?
Yeah.
Okay.
Yeah. So any more arguments here? I mean, any more doubts?
It's okay.
No. D part here.
X sin x, x square plus 2.
Mhm.
Again, same thing only x sin x is also continuous, and 1 by x square plus 2 is also continuous, therefore it is all continuous.
Okay. All right.
Yeah.
I'm sorry. Okay, next we have now limits of continuous functions. So let's look at this theorem here, theorem 10. Here we are on theorem 10 basically. The limits of continuous functions here we have, right?
Yeah. G continuous.
If g is continuous at the point B and limit x tend to c f of x is equal to b, here we have.
Yeah.
If g is continuous at the point B and limit x tend to c fx is equal to b, so we can say limit x tend to c g of fx is equal to g of b. That's quite logical. Because limit x tend to c f of x is equal to b, so we can say limit x tend to c g of fx is equal to g of b, or that is equal to g of limit x tend to c f of x.
Okay, 1 second. Fine. Sure.
Okay. Now, proof is fine. You can do by yourself. Okay. Have you got the statement here?
Yeah. Let me copy down.
Yeah.
Okay. If G is continuous at the point. Ah, yeah. So you're applying the limit. I thought you would apply the limit to both of them. I thought how you would do it is lim of G of lim of.
Okay. Okay. It is the same thing only actually. Now,
Because I thought what would happen is this multiplicative rule. I thought what you would do is literally have a limit here also. Lim,
okay. Now here we have example line basically. Example line here we have now. So we have the following calculation here we have.
yeah.
Limit x into pi by 2, here we have cos of 2x plus sine 3 pi by 2 plus x is equal to cos of this. So can you just solve it out on your notebook? The function goes outside and the limit can be taken inside now here. Why? Because this is all continuous, so cos of this also be continuous. Okay, so we can take limit inside the continuous function. Okay,
Yeah, let me just copy it down.
it's a very important theorem. Otherwise, you will not be able to solve this question. Application of theorem 10. Yeah.
I'm copying on the example so that I can do it. So okay, you are saying that cosine of whatever that is the g of x, and sine of 3 pi by 2 plus x, that is your f of x,
Okay.
right?
Um, see, you have taken limit inside here, okay?
Yeah, okay, okay, wait. You are putting the limit
In,
on both of the two.
inside the cos. Because we have this complete function is continuous.
That is not one function, no.
No, that is fine. I mean, one is this 2x here we have. Second, this one. So both added become continuous.
Okay.
So continuous, this is one here we have. So cos of continuous will also be a continuous function. So we can bring limit inside as per theorem 10. So limit now x tend to pi by 2, 2x is given as pi here we have. Plus limit here we have x tend to pi by 2, here we have sine of 3 pi by 2 plus x. That would be sine of 2 pi. And that is 0. So it's coming out to be cos pi here we have, that is minus 1. So cos pi is equal to minus 1 here we have, that's the answer.
Yeah.
Now next we have
Wait, why did sine 2 pi equal 0?
sine 2 pi, look at the graph.
Right, okay, like that. Okay,
Yeah,
okay,
yeah.
okay then.
No, I mean in any way you see, look at the graph, look at the unit circle, it is coming out to be 0 only.
Yeah, you just did directly from there.
Yeah. So now here we have now intermediate value theorem for continuous functions. Now here we have theorem 11 basically. Theorem 11 is the intermediate value theorem for continuous functions here we have. It says that if f is a continuous function on a closed interval a to b, and if y0 is any value between fa and fb, y0 any value here we have between f of a and f of b here we have, then y0 is equal to fc. So y0 is equal to f of c for some c in the closed interval a to b. Let me again repeat. If f is a continuous function on a closed interval a to b,
Okay.
and if y0 is any value between f of a and f of b, so f of a here we have and f of b here we have. So y0 is any value here we have between, so y0 is lying between f of a and f of b.
Okay.
Then we have y0 is equal to fc here we have, y0 is equal to fc for some c in the closed interval a to b.
Okay.
For some c here we have in the closed interval a to b. Just hold for a moment, Sana.
Yeah.
Okay, yes, Sana. So here we have y0 lies between here we have f of a and f of b.
Yeah. Okay. So it is between those 2 points. So this point cannot be part of that point.
Yeah, absolutely, yeah.
So these points cannot, it does not come under this theorem.
Yes. So it is actually here we have, so y0 is lying between here this point and this point basically. So this and this. So therefore y0 is f of c, where c is the point that will lie between a and b. So c lie between here we have closed interval a to b. C lying between here we have closed interval a to b, okay?
Yeah.
Now let's go through here example number 10, okay?
Yeah.
Now here we example 10 basically. Show that the root of the equation here we have x cube minus x minus 1 equal to 0. Between 1 and 2 here we have. So let's show that here that the root of the equation x cube minus x minus 1 equal to 0 between 1 and 2. So here we have that fx is equal to x cube minus x minus 1. Now since f of 1 is equal to 1 minus 1 minus 1, that is minus 1, here we have less than 0. And f of 2 is 5 greater than 0. That means first we will find out two extremes here we have. We are finding out here we are doing the theorem only. We're finding out two extremes here. First is f of 1, that is giving a minus 1 value here we have at
Because you're saying that for there is a root because
yeah.
uh, there is, you can show that there is minimum one root between these two values because there's a sign change.
Yeah. So here we have actually f of 1, it is coming out to be here, the value is minus 1 here we have, right? And f of 2 here, it is coming out to be equal to the value is given as how much? 5 here we have. Are you getting it?
Yeah.
At f of 1, the value is minus 1. And f of 2 we have, the value is coming out to be 5.
Correct. Now you cannot use this to say
Mm-hmm.
that show that there is a root of the equation x cube minus x minus 1
Yeah.
between 1 and 1, instead of 1 and 2 you are saying some other two values where both of the values are positive. Yeah.
Yeah.
Right. So instead of getting my the answer of f of that to be negative 1
Mm-hmm.
and the other it's instead of having minus 1 and 5 you
Mm-hmm.
have 1 and 5. Okay.
Yeah.
But even then there is a root. How do you pull it? Okay, I'll just
No. That is quite obvious. That is what there will be root. Yeah, absolutely. It is logical, mathematical logic. If you go from negative to
Yeah, but
positive value, there will be at least one root. At least one root.
so imagine you're taking these two values.
Yeah.
Um, say that is 1,
Yeah.
like something like this.
Hmm.
This is meant to be more like this, but you get
Yeah.
the point. Uh, both of these values, if you substitute them, they'll both give you positive.
Yeah.
But the function, you have to still prove that there's a root or
Hmm.
multiple roots.
Okay.
How do you do it?
Multiple roots.
So wait, I'll give you a proper thing.
Yeah.
You have you have this thing,
Hmm.
something.
Yeah.
Then you are done. Uh, 2 points, this one and this one.
Hmm.
Yeah. So
Yeah.
this is -1. This is 1.
Hmm.
Okay.
Yeah.
Um, both of the y values, they say 5 and 1. They are
Hmm.
both positive.
Okay. Okay. Yeah.
But if you use this, then you will not be able to.
You are not sure. You are not sure that there are multiple roots.
You do not know if there is root or not.
Yeah, your argument is right. I agree with you. Yeah. Yeah.
So you cannot use this you cannot use this rule to do much.
No, 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 no. Here the value is going from -1 to 5. One is positive,
Yeah,
one is negative.
yeah. Given that that is happening, then only you can know.
Yes.
Otherwise, you cannot know.
Yes. In this solution, we are given that. See, we have two extremes now. Here we have, look at domain, here we have two extremes. One is this extreme, second is extreme, left extreme and right extreme. Between left and right extreme, you're getting a root here. It is
Yeah.
given, yeah. Yeah, but if both are positive or both are negative, then we are not sure.
Okay.
Yeah.
So if they given, so if this turned out to be 1 and 5, then we would not know.
Absolutely, yeah. But it is -1 and 5 here we have.
Therefore, we know.
Yeah, absolutely. Your good question, yeah. I mean, that makes sense, yeah, absolutely. Okay, now here the example 11.
Yeah.
Just go through that and try to analyze what is solution here.
Okay. This thing was.
Okay, here we
Can you
have.
just- Yeah. Go ahead. Go ahead. Please go ahead.
Use the intermediate value theorem to prove that the equation square root 2x plus 5 is equal to 4 minus x square has a solution.
Yeah.
So we now rewrite the equation as square root of 2x plus 5 plus x square is equal to 4. Okay. And set here fx is equal to square root 2x plus 5. Here we have yellow one, right?
Yeah.
Plus we have x square here we have. So, and this blue one here we have. So what we're doing actually, we just divide the graph into two separate equations. Okay. 1 we're making here root of 2x plus 5. So this is gx here we have, yellow one. It is continuous, you can see here. On the interval minus 5 by 2 to infinity. My question is why it is minus 5 by 2? Why not minus infinity?
Because after that it is like root of negative also.
Here root of negative is not possible. At minus 5 by 2 it is 0. So therefore we have starting from minus 5 by 2 to infinity here we have. Since it is a composite of square root function with a non-negative linear function y equals 2x plus 5. Now f is the sum of function g, and here we have one quadratic function, that is x square. That is actually 4 minus x square. So this here we have and this here we have. This one is this function here we have 4 minus x square. Now thing is that when we equate this and this, we will get an intersection. Are you getting my point? Whenever we equate the mathematical equation of two functions, we get the point of intersection.
Yes.
I'm again repeating.
Yes.
Whenever we equate the mathematical equation of two functions, we get the point of intersections. Now here we equate this 4 minus x square and square root 2x plus 5. We get here the point of intersection.
Yeah. So if you were to solve it, you would get 4 is what the point is.
I mean, whatever we get basically, so we have here, this is coming out with this, is continuous on the interval here we have, minus 5 by 2 to infinity here we have. Now by trial and error, we find the function values, f of 0 is equal to root 5. Now f of 0 is coming out to be root 5 basically. Okay, you put here x equal to 0, you will get root 5, 2.24, and f of 2 is given as 7. So what they're doing actually, they're taking us to extreme here we have. Are you getting the point? They're taking to extreme here because we're using the intermediate value theorem. Okay, so one extreme, the left one is we're taking x equal to 0. Second extreme, we're taking x equal to 2 here we have. So we got the value as 2.24. Here we have 2.24. Second we get 0 actually.
Okay. But why? Like why do we do that? Because you have okay.
Because we're going to use the intermediate value theorem actually, as the question specified.
Can we go through this a bit more? This is just messing me up a lot. You not understand.
Okay, let me give you a very simple method here. Okay,
Yeah.
all right.
Can you just write this entire thing, but properly with steps?
No. Yeah, let me just give you a very simple straightforward solution here we have. This y value here we have, this one. X here we have now. You take now one function here y1, that is root of 2x plus 5. This you have, this one here you have y is equal to root of 2x plus 5. y1 here we have. Next is y2 you have.
That is
y2 is 4 minus x square here we have.
and then you have yes.
So here we have now. That is 4 minus x square here we have. Now the one is here we have y equals root of 2x plus 5 here we have. Next is 4 minus x square here we have. This is the point of intersection here we have.
Yeah.
Now when they intersect here, this solution need to check whether it exists or not using the intermediate value theorem. Okay, yeah, so what I can do here, we take now two extremes. One is x equal to 0, second is x equal to 2. These two extremes we have taken here. And now let's first find out basically the value of y1 at x equal to 0. This y1 here we have. So y1 at x equal to 0. Because in intermediate value theorem, we take two extremes, the left one and right one. And then we find the intermediate value. So y1 at x equal to 0 here we have. That is coming out to be equal to root of 5. That is 2.24. Okay. At this point here we have 2.24. Now next we take the value as x equals 2 basically. For same function. So for x equal to 2 we get here.
Why do we? Why do we?
Because in intermediate value theorem we always take two extremes and then we take the intermediate value. See, let me just
This,
yeah.
that two extreme could be anywhere else also, no?
That two extremes could
It
be
doesn't have to be. It could
No,
be
no.
also -1. It could also be 3.
yes. It could be. No issue. You can take -1 also. Yes. No, but you will not take 3. Yeah, you can take 3 also. Yes. On the left extreme you can take -0.5 also. No issue. You can take. Yeah. You can take.
Yeah. You're taking it because you know that the intersection is between those two things.
Yeah, that is clear from the graph. Absolutely. Yes.
Yeah, but we don't know the exact point of intersection. That's
Absolutely. Yeah. Absolutely. Yeah. I'm agree with you now. Yeah.
okay.
Yeah.
We find those two values and you substitute, you get 2.24 and 7.
Yeah.
And because 4 is in between those two,
Hmm.
but where did that come from? That because 4 is in between those two. That I didn't understand.
4. Which 4 are you talking about here?
Because in the here now. The question.
Hmm.
And, you just continue with your method and you just continue doing it and I'll ask you a question.
Okay. So now y at y1 at x equal to 2. Okay.
Yeah.
That equals we have as it, at this value here we have that is coming out to be equal to how much at x equal to 2. So that will be equal to here we have root over
So 9.
2x plus 5, right?
That's root of 9.
Root of 9. That is given as 3 here we have. Now between 2.24 and 3, between y1 at x equal to 0 and y1 at x equal to 2, there will be here we have one point of intersection. Are you getting the point?
Yes.
That we can take it as y1 at x equal to c. Are you getting my point?
Yeah, that's fine.
And from the graph, it is very clear this c is lying between 0 to 2. Getting my point? So hence it is proved that intermediate value theorem is verified in this graph. So we can say that it has a solution.
No.
Hmm.
Now, what you have proved is that the intermediate value theorem can be used.
No.
That is
I have shown you actually the intermediate value theorem. Yeah, can be shown, can be applied actually. That's what I proved. Yes. And one more thing. One more thing I have shown to you, that C lying between 0 and 2, close interval.
correct. Now, but here, this and last thing, if you look at the question,
Hmm.
I'll highlight it again. That since the value is between that thing,
Hmm. Yeah.
can you read that? Does that make sense to you?
Okay, let me read. See, here we have since the value y not equal to 4 is between the numbers 2.24 and 7, where the number c belongs to 0 to 2 such that f of c is equal to 4. So number c solves the original equation. It makes sense, yes. It makes sense, yeah. That's what I was saying. Yeah.
Where did the 7 come from and where did the 4 come from?
No. See, thing is that actually you forgot about 7 and 4 actually. Forgot about 7. You take here 2.24 and 3. You forgot about it.
Okay, fine. Now, they are saying that you have to prove that the equation has a solution.
Mm-hmm.
You have still not proved by your method that the thing is having a solution.
No, why it is not
Because
proved actually?
not until this point. You have proved it until there.
No,
At
no,
this
no, no,
point,
no.
that is not the
You,
solution.
no. You just forget about it. You come to the solution here. The solution. Does the solution make sense to you? You forgot about that.
Yes, that makes sense. Now you have proved that the theorem can be used.
Oh, yeah, no. Wait, pivot theorem can be used. Also, we have proved that the C belongs to 0, 2. So C gives
Yeah.
the solution. We have proved that.
So you
C
are
is the solution. We have proved that. Yeah. Yeah.
uh, so you're saying that the solution is that uh, there is a value at which there is an intersection
Mm-hmm.
between zero.
Okay.
You're saying that there is a. You are proving the solution by saying there is a solution between 0 and 2.
Okay.
That is what you're doing. You're not actually finding out the solution. You're just saying that there is a solution.
We don't need solution. We don't need solution here. Solution is not required here. We have.
You are just saying.
We have to just
that
prove, yes, the solution is not required. We just have to prove that there could be a solution or not using the intermediate value theorem. Using the intermediate value theorem. And we have proved that we got a value C which lying between the two extremes 0 and 2.
Okay. Now,
So,
can we do one thing? Can we try and find the solution?
wait. Yeah, please tell me now.
Can we find the solution?
So, I mean, solution is, you can use calculator or something like that. You can find solution. Yeah, why not?
That is fine. The
Yeah.
thing is, they have not. I don't think they have done it that way because they are saying that the value is 4x. They are saying that.
No. C, we don't know. C, we don't know. C lying between somewhere 0, 2. Solution finding is not our purpose here in this question, but you can find out using calculator or any manual method. Thing is that, but C lying between 0 and 2, that's what intermediate value theorem says always. C lying between 0 and 2 here we have.
Okay.
Yeah. So we're done for today.
You have,
I'm sorry. We have next class at 9:30 p.m.
yes.
Okay, that's great. So meeting at that time and we'll continue with these topics. Okay.
Sure. Okay.
Okay. Thank you so much. Bye bye.
Yeah. Okay.
Bye bye. See you.